with any luck, I will actually get to stating the regularization theorem after having defined what a bundle and a Fredholm section is in the polyfold context, which I advertised I was going to do this at the level of PSS moduli spaces, and then I retreated to SFT spaces, and then I retreated to Gromov-Witten spaces, and now I'm going to retreat to Morse spaces. Just because that's how we did the pre-gluing and anti-pre-gluing, and that whole splicing situation was just a little easier. I'm pretty confident that if I locked you up in a room on your own and said, now write it down for Gromov-Witten, you could do that, having notes like this. So my plan is to try to do this exercise and actually exhibit a polyfold Fredholm section for a very, very specific Morse theory, namely one where there's just one critical point, 0, and I want to look at Morse trajectories of finite length or infinite length. So there's going to be some that just flow by and have some kind of length to L, and then they might break. But this being a Morse function and Morse flow always going, decreasing in the critical value f, it can only break once. So the worst thing that can happen is one breaking. So I actually get a finite construction of the topological space, right? If you believe me that pre-gluing actually gives me a topology there. And so I should start with something that's a second countable metric space, and that's something one would need to check. There's the Gromov-Hausdorff distance between the images. That's already a metric. That doesn't quite resolve this thing completely because, right, that's the one cool thing here is there's a whole lot of points in here that all just map constant to 0. And so for every length, there's a constant trajectory there, and also there's a broken constant trajectory. And so I'm going to have to add the length parameter to get a metric. Should all be doable. Right, so, and now I'm going to be sort of a little bit schizophrenic, right? I sort of explained polyfolds in terms of a category. We had object spaces, and the transition maps really were the morphisms. And I'm later on just going to copy definitions from a write-up where we don't have that category thing. So X, with or without these lines, is the topological realization. And I'm going to be very careful to write objects of X when I mean object spaces. So, right. So, we need, if this is going to be an M-polyfold, we need charts, and then we need to understand the transition maps. So, charts, near a finite length trajectory, I'm going to write that down so we can look at the transition maps in a moment. So, and that's there's something a little bit funky going on. So, I'm going to take, I should take a Banach space, scale Banach space. So I'm going to throw the length in as one parameter, and then since I'm in Rn, I can vary these things by just adding. So this is my scale Banach space E. And now I'm supposed to take an open subset in that and map that homeomorphically to a neighborhood. So my open subset is going to be, so I'm going to change the lengths by a scaling factor somewhere between 1/2 and 2. That's the basic idea here. And I'm going to take some small vectors. Oops. can add. So I would like this to be homeomorphic to a neighborhood of my gamma 0 in that topological space. And the way that goes is scaling factor and vector, right? So this would just be a different trajectory of the same length. And so now I have to convince myself that I can actually get all nearby trajectories by first changing the trajectory and then rescaling it. Right, so this is now of length theta L, or minus 2 theta L. Right? It's my ambient space Rn. So. I don't know of a way. I mean, this is also slightly problematic in terms of differentiability, right? But since shift was okay, yeah, for scale smoothness, probably rescaling is also going to be okay. Okay. So what's going on here? Right. Yeah, I want to call this. So why is this an M-polyfold chart? Right. So this here is an open set in E, and it is also the image of a retraction where the retraction is simply the identity. So correct, yeah. Scale Banach manifold charts are also M-polyfold charts. So scale Banach manifolds we got by taking local models in open sets. Taking the trivial retraction, we reproduce that. So now, of course, we want to do the more fun thing. And right, what I did do last time, I think, is I wrote a very special chart down for this near the trajectory that's constant 0 and 0. So I kind of forgot adding extra gamma zeros in every way. It's not going to change a whole lot, but I'm going to try to be a little bit more honest. So I have a center point that's now actually a broken one, and now I need to vary with a gluing parameter, and I'm going to, well, yeah, if I have a nearby broken one, I'm going to need the whole half interval worth of a section really in the pullback bundle to add. Fortunately, my pullback bundle is trivialized here. So I take H1 maps. I am going to, oh no, I'm not going to shamelessly call the whole thing a Banach space. So this is my scale Banach space now. And I would like to parameterize a neighborhood of the broken one. But the game is now, right, I don't need to take an open subset in here. I can retract. So use a retraction or a splicing in this case. To my subset O, which is going to be, right, so for all gluing parameters, well, you know, translated into a finite interval, just that point times, well, you know, the image of my projections. So this map is given by a family of projections. Oh, the other way, right? R of V was the notation. So there's the gluing parameter R is secretly in the picture, which is large when V gets small. And that really is my retraction. and that's defined on this whole space, so I'm kind of just going to call that whole space U in this case. And right, so this projection was, well, it projects to, well, the image of that projection in every fiber over V, but we constructed that so that that was the kernel of some minus gluing. So minus gluing was somehow the thing that kept track of what plus gluing loses in terms of information. And so here we're just taking the vectors where plus gluing doesn't lose information. And then from here, I'm getting my homeomorphism, which maps gluing parameter and pair of vectors to the preglued guy. Right. So this is not an open subset. That's an open subset. There's a retraction onto this, and a homeomorphism to that neighborhood. Oh, and that's a lie. Right, that was exactly dumb. I should add gamma 0 minus plus this, and gamma 0 plus this. Right. I need to change the center path, before I plus glue. It doesn't matter actually. I could either, this is a linear operation in a linear space, so I could either write it this way, or I could write it as a plus gluing of this pair, plus the plus gluing of the X's. In general, of course, once you're in a manifold, that doesn't work so well, so there's all kinds of exponential maps in the picture. Right, and so we remember to what extent we should be scared of these projections. Right, so any one projection is given by a whole lot of shift operators on the gammas, multiplication with cutoff functions. There's the projection operator here, and then we invert the matrices that were here. So, in that same writing, what this plus gluing, I guess, just on so as an operator is, right, is you're shifting these two vectors in different directions. And then you are multiplying it with a one-row matrix, namely beta and 1 minus beta, which is the first row in that matrix. And the second row here just gives me the minus gluing. And in this case, I could have forgotten it because I'm multiplying it with 0 afterwards anyways. Just nice and symmetric. So that's the more honest version of the polyfold chart we constructed. It's, well, let's see, it's a homeomorphism pretty much by construction, because that's how we define the topology on our space, via the pre-gluing. And so here the pre-gluing is the map. So really all we needed to make sure is that it's injective. And that's what we did by this weird restriction. So, right, so these are charts, and if I go into the category thinking, then really I should take the disjoint union, somehow cover my space with hopefully maybe a countable number of these charts, some centered at smooth paths and some at broken paths. And so then the object spaces are the open sets in the scale-Banach space from the first one, and this splicing cores are images of the retractions from the broken ones. So that's my object space, and then I ought to understand what my morphism space is. And that's the same thing as understanding transition maps between these charts. So here, really, right, if, in order to go back and forth between morphisms in the category, you want to look at the source and the target map, right? They both map morphisms to objects. And in order to get the transition maps, you're supposed to take source inverse that gives you a morphism, and then target back. And of course, that's not a well-defined map. That's only a well-defined map when you restrict yourself to some small set in the morphism space. And so those are exactly the bits and pieces that contribute to these transition maps. Or differently, the transition maps, right? The transition maps between these charts give you connected components of your morphism space. So right, so there's two types of charts, which means we have three types of transition maps. So the first type is just one of the open sets. So this is when both centers, when both charts are just charts for finite length trajectories. And just for shits and giggles, here is the transition map. It's not entirely pretty, so that's right, the scaling parameter and the difference vector, and since the two charts might be centered around different lengths, I have a adjustment of the lengths, and then I have, well, I start with, what is this? Right, I start with phi j, and then I do phi I inverse. So phi j is the one that adds to the gamma j map and rescales, right? And then phi inverse rescales back, and the total result is rescaling by this constant. And then I have to subtract the center of the other chart. So what I would like to say is that this is scale smooth. And I was previously a little bit afraid of this rescaling by theta. But the nice thing now is that I'm just rescaling by a constant. And that's perfectly smooth. So turns out here, right now, the transition map here is not that bad, actually. So this is, in fact, not just smooth, it's in fact C infinity on HK for all k. But that's just bonus. Well, I mean, that's exercise, if you're smooth on every level of a scale Banach space, does that, prove that means it's scale smooth. So.
Should there not be like a theta inverse in the argument?
Here. Yeah. Right, no, because I'm, let's see. Right, so the map takes, so the phi j first takes this to, in fact, this at theta inverse star. Right, but then I'm going back to my chart, so I'm taking the inverse of, right, so let's think of this as gamma j here, right, and then I'm applying an inverse to get back here. And I don't yet know what the new theta is, right, but I'm going to decide that from what the length is. And it turns out that the new theta is just the old theta in the j components multiplied with this correction factor. So I need to sort of undo this and read off the new theta. So the new theta is here. So what's really secretly in here is, I guess, And if you call this theta prime, what secretly this is theta prime. I'm not sure this is times theta inverse. Right, that's what that factor is. Right, that's sort of a common, source of confusion, because when you write down your ambient space here of the M-polyfold, it looks like it by itself already has smooth structure. And so you'd like the chart map to be smooth, right? But that's not really what we're doing. We're only thinking of our ambient space. The M-polyfold is a topological space, so it's really useful to kind of force yourself to keep forgetting that there's sort of a smooth structure that stays in your face. So, right. So when you see this union here, every little piece looks awfully, nice. But try to think of this only as a topological space. So then, the chart maps are homeos, and really we're just interested in the differentiability of the transition maps. So, okay. So that was the simple one. The good news is it's not going to get a whole lot worse. So, especially now that we have a formula down here. So now I want to go, right, I want to compare a broken chart. Right, that's, nobody on blue jeans. So that's my chart in the near a broken one, right? So this, right, the chart here really is from the not quite open set O to X. And here I have UI going to X. And those are the same spaces, so my transition map factors through there. And I'm getting that defined just on an open subset of this splicing core, curly O. And, right, so what does that do? There's something after I have some space. So, right, so points in my splicing core again are gluing parameters in two maps. And now I kind of need to do exactly the same thing that I do here, except for sticking in the chart map from the UJ, I'm sticking in the chart map from this gluing. So here's the glued guy. And, well, just this doesn't get rescaled, right? And then I ought to apply the inverse of my chart to the, interior. So I'm only going to look at this in a domain where the gluing parameter is finite, certainly. Mm-hmm. And so these are going to have length 2r. UI might have a different center length, so I need to rescale that to that length. And then, just like here, subtract the center of the chart. So, what is this? Right, that's a map a priori that's only defined from O to U. And in order to check whether that's an admissible transition map, I need to compose it with RJ. Right? So the actual transition map that I need to look at is project down to the splicing core, then take my transition map. So that's the actual transition map I ought to be wondering about. But what I'm doing here is, right, so I have my projection, and that's exactly this here. That's this massive operator. And what does that do? Right, it does plus gluing and minus gluing, and then it, sort of projects, forgets about the minus gluing, and then applies something inverse to the existing thing. So really, geez, what's going on here? Right, yes, okay, so from here to there I'm changing my vector a little bit so that its plus gluing stays the same and its minus gluing becomes 0. But what I see in the formula here is just the plus gluing. So if I start with an element up here, right, and stick it in and first apply the projection and then apply this map, I actually get exactly the same formula, because I'm projecting along the kernel of the plus gluing. So beauty is that it's the same formula. So all I need to check now is what here, that what we did claim to have checked is that this kind of big composition is scale smooth. Plus gluing had a very similar formula, and the only extra thing that happens here is I'm sort of scaling and not just shifting with a varying parameter. But that's an exercise to go through in scale calculus to check that that map is also scale smooth. Hint, use the chain rule, right? Write it as a composition of a number of scale smooth maps. So, okay. And then of course, this is the hard direction of a transition map. There's also the other direction of a transition map if you want to try and think about the transition map from U to O, right? Then you're supposed to pre-compose with the projection on this side and then just include into space here. It's not so pleasant because I would have to invert the plus gluing as an operator, but we know how to do that. We've done that for the construction of the splicing already. So there are formulas for that as well. But it's probably easier to just check that this guy is scale smooth and actually a diffeomorphism in some useful sense, as it has sort of maximal rank, so that the inverse will be scale smooth as well. Yes, another lemma in scale calculus. So that's two transition maps, and the last one is what if I have two broken guys. So that's a situation where I have one splicing centered at some broken thing, and another splicing centered at another broken thing. If I'm looking at the transition map in this direction, I actually only need to know the projection map on the first side, because here I'm just going to use the embedding. And so this is the map that I'm actually interested in. And again, just to demonstrate that there are formulas, they're here. Let's see. yes. I do want to try and write that out first. So, right, so what is happening again? V xc minus xc plus goes to what? Well, phi I inverse of phi j, and phi j was the plus going. So at gamma j. And so now, oops. So phi I inverse now is the map that tries to find the element in the kernel of the minus gluing for that particular chart. Right? So it takes whatever this thing is and calls this the plus gluing. So this is sort of the plus gluing in my I chart of something, and I'd like the minus gluing in my I chart to be 0, and then that should give me whatever that something is. So this looks very similar again to, sort of just inverting this matrix that is given by plus and minus together. And so that's exactly what's happening here. So solving this equation is that, and just the pre-gluing here is this part. In this case, I've actually killed the anti-gluing here. So that's, yes. These zeros here that's this 0. And formula that looks not terribly crazy. This just shifts by Rj, and then shifts back by some other gluing parameter, R prime, that's related to V prime, which I'm now supposed to somehow read off from this also. Right? So there's an R prime here. And, well, if these are actual Morse trajectories, I can look at the Morse trajectory and ask myself, well, what is the length of it? So, so on that level, that should be the identity. However, we've made these choices of translating finite length intervals to, infinite intervals. So. With the gluing profile, and that's going to get us screwed up here if we take different gluing profiles for the different charts. So what I would like to do here is I would like to get V prime to just simply be equal to V, and I get that if I take the same gluing profile. There's a map here, right, Ri, and a map Rj, and I'd like them to exactly be the same. Depending on, well, how large a number they're defined up to. And so our preferred choice is the one for which the splicing was actually scale smooth, which is this exponential guy. And I think, right, this is made exactly so that it maps, right, if I put in V equal to 1, it maps to 0. And I think that's the only reason that I have a minus E in here, because we would like, some sort of nice standard intervals identified. And 0 goes to infinity. So that means you really, if you don't want to fix this formula, but somehow allow yourself slightly different formulas for which maybe your splicing is also smooth, you're kind of getting different atlases on your M-polyfold, which may or may not be equivalent, depending simply on, what the transition map is for this very, single variable problem. That's really where this whole trouble goes to. It's really just the sort of problem with transition maps only goes. Problem with transition maps that comes from gluing profile really only is visible in this gluing profile. And possibly also in this formula, right? But so at least with this exponential gluing profile, and this multiplication of matrices here looks very similar to the one that we had for the splicing. Right, that was this projection. The only thing is, that projection is already in here explicitly. So really, all that I did here is I took slightly different cutoff functions on the two sides, and so you can, crank that out, get a formula that looks pretty similar to the one I painfully written out here, and hopefully have enough core elements that are scale smooth that you can just sort of quote your scale smoothness together from the chain rule again.
So the first two transition maps, we always end up like recentering by subtracting off like our gamma.
Right.
There's no need for that here.
Oh boy. No, of course there's need for that. Yes, that's good observation. Right. I mean there's that center here, and I should now recenter. Yes, indeed. So minus gamma. What's that? I minus and gamma I plus. Right, but the nice thing is that, you're recentering really after all the hard stuff has happened. Right? So.
What does it mean to subtract?
Well, these are maps to Rn right now, right? Yes. So that's the reason I went into Rn, so that I could just write this. Right? Eventually, when you're in a manifold, subtracting means taking the inverse of an exponential map, right? Which means you want to be somehow close to, or you want to be within the injectivity radius. So there's a whole lot of technical complications once you get into curved spaces. All right. So we have a full and complete M-polyfold. One-page construction. Well, modulo some lemmas in scale calculus that say that certain formulas are scale smooth. And checking that everything I claimed was continuous actually is continuous. Okay, but what we really want is a section, right? So we need a bundle and a functor between those categories. So what should I do? Right, well, I need another category over here, and then I need a map, at least one between the realizations that hopefully comes from a functor. And this, right, so now we're doing Morse theory, right? But I'm going to do this as if the Morse equation was a PDE. So here's my differential operator.
I had one more.
Yeah.
Quick question. In that last transition map, you take you pre-glue, and then when you take the chart, the inverse of the chart.
Right.
Your R variable can change. You have like an R prime, but
right.
When the shifts, the x's minus and plus, will those also change?
The x's, oh yeah, the x's is exactly what, I mean the x's are the vectors, right?
Yeah, but will they be different scaled when I go to a different, like I'm taking one pre-gluing, but then when I take the inverse chart, I get a different pre-gluing, will that also affect the x's that I'm...
Oh yeah, sure, I mean that's this whole matrix here, okay? I mean one thing you can imagine is even just having the same, where are we? Right, if you take this chart here, if you just take a different, well, if you just took a different center, gamma 0 minus gamma 0 plus, then really nothing much would be happening. But you could take a different cutoff function beta. Right? So, well, let's see. If you had the same cutoff functions and the same gluing profile, then what this here is really the splicing projection. Which makes sense because it's the splicing projection and then the identity somehow. Right? But the place where this becomes interesting is really when, well, yeah, on the one hand, if you have different centers, you see that one gets sort of added before you do all this, and then the other one gets subtracted afterwards. But since in this case it's all linear, right, so if the betas were the same, then in fact this would just be somehow, I think, the identity on Xi minus Xi plus.
But because you chose different.
Except, no, right, sorry, it would be the splicing projection on Xi minus Xi plus, right, because we do this first. And that's, this formula here exactly is the splicing projection if you put the betas to be the same.
Okay.
So it's the splicing projection on Xi minus Xi plus, and then some, recentering the map with the gammas. Right. We've made the gluing parameters be the same. We do allow different cutoff functions beta though. So it's not exactly the splicing projection because this is a beta I and that's a beta j. Good. All right. So, okay. I need to write down my section. Right. Yeah. And in order to write down the section, I first wonder what the fibers will be, and so it's good to know what elements will have to be in the fiber. So always this, same mystery of having two completely different fibers over my polyfold. So now, how do I get that to run? Well, right, I have this is my chart near an unbroken one. And now I need to first decide what my fibers should be. Well, in this case, somehow the obvious fiber bundle over this that a differential operator should have, or first order differential operator should have values in, is exactly the open set here. So U, and then times not H1 but H0 functions on the same domain. So there's a second scale Banach space F in the picture here. And then in order to understand what my section is, right, so this has an obvious projection down to U. Right, and my section somehow comes from what I think the section should be, together with a chart map somehow for the polyfold. And the slightly confusing thing here is, right, that elements in here are these pairs theta xi that really get rescaled. So then this is stuff that I'm applying the differential operator to. I get somewhere, I get into H0 with varying lengths. but I want the chart for my M-polyfold bundle to trivialize the fibers, and so I'm gonna just rescale back with a theta to get to standard length. So really what the section becomes in this is identity on the first two, and then so what happens with the rescaling factor is that it sort of multiplies the d by dt. Plus or minus gradient f. I think I decided on a minus gradient f. So I'm looking at gradient flow lines. This applied to gamma 0 plus xi. So perfectly nice differential operator on xi. I'm just using the time scaling parameter to shift to here. That scales the differential operator here a little. So that should not look scary, right? That looks like a family of differential operators of first order parameterized by theta. But theta is somewhere it's not zero, nor is it infinity, so perfectly nice, smooth family. And somehow I need to now understand how that family matches with the family that I want here. Right. And I should not do that here and try to let theta go to, what is it, infinity. Right? Make this long. And that looks like multiplying with 0 here. That's not the right way to think about that. The better way to think about it would be probably to make the lengths get larger and larger. But the best way to think about it is to, whenever you want to think about something in the neighborhood of a broken curve, it's best to think about the chart around the broken curve. Pull everything back there. So that's exactly my chart map here. The splicing, and same game. I need to first decide what my object space should be. And this is exactly where I have that problem. I need to jump in dimensions. So, and I'm going to try to do this by also using an anti-pregluing. So I'm going to take my object space to pretty much be, I'd like that to be ideally just the base or a fiber product over the base. The base is already this weird space here of the splicing, but why not take the same thing? And now I need to decide what my fiber is. And since I somehow need the same thing that happens to jump from sections or from maps on a finite interval to pairs of sections on infinite intervals, I'm simply going to take exactly the same splicing again. I'm just going to call it capital Pi. And I'm going to declare it the same formula. So as little pi, with the one difference that it needs to now act on this fiber f, which is H0 sections and not H1 sections. So, so this here was part of E. What we have here is black 0 V0 times E, and then F. So this, the splicing here is going to be, well, the pairs pi little pi and capital Pi with the same gluing profile, right? And the only thing is that this here starts at H1 maps, whereas this starts at H0 maps. So I guess what I can say is when I restrict capital Pi to the dense subset of H1 things, which is sort of that's the shorthand for that is the scale F sub 1, right? Whereas H0 is the scale F0. So that's a dense subspace, right? And on that I just define it by the same thing. And then it has a unique linear continuous extension. So so very tightly connected bundle space, right? And then with that, again, I need to remember what my chart map really is. Oops. It's not going to get pretty there. Right, so chart map is the plus gluing into the polyfold, right? And the other thing that's good to keep track is, so the map is the plus gluing, and the minus gluing by definition is 0. And then I'm supposed to apply, right, so this I'm supposed to map to here, identity on the base, and now I'm expecting some kind of differential operator on the fiber, or that gives me values in the fiber. And that should come from, the section that I imagined being the differential operator in two components, at gluing parameter infinity, and in one component at gluing parameter 0. So, sorry, at gluing parameter finite. So, let's see. Right, so at infinity, it's pretty clear what I'm supposed to do. Well, so that's the definition here, right? So at infinity, I'm just going to apply my operator on both components. Oops. On both components, but I'm shifting by the center. Damn, that does not look good. That looks like pre-gluing. So it's a pair that's going on, right? I take gradient equation on the first component, and then I take gradient flow equation on the second component. There. And now in the second component, well, so part of me wants to just write down the gradient flow equation on the pre-glued curve. But that's certainly some part. Oh goodness, I keep forgetting my shift. For some reason I decided to be anal and have that shift in. And so the centers. Right, so this is certainly what we'd like to solve for. Right? However, this is a map, now since I'm at finite gluing parameter of finite length. And so it doesn't even lie in the fiber F, which sneakily, I didn't even tell you what F is. Right? I should maybe say what F0 is. So F0 will be H0 from 1/2 interval to Rn times H0 from the other half interval. Standard scale structure on it. So this operator, or this vector field, does not actually lie in either one of these components. Where it does lie is in H0 of a finite length, which is in the target of this isomorphism. So this, right, is being mean here, right? So this is my old splicing, right? Plus and minus gluing together on this space E, which looks very much like this, except starts at H1, gives me an isomorphism to finite length paths and infinite length paths that keep track of the kernel of the plus gluing, right? So pictures here, right? So really, well, there's a pre-gluing of the center of the curve, and then the plus gluing of the x's really changes that path a little, with a pink interpolation part, right? And the bits and pieces of xi minus and xi plus that happen very close to 0 are forgotten here. And so I can keep track of them by their minus gluing, which looks a little different now than previous time I drew it, because previous time I drew the minus gluing of the path itself. Right? So here I'm not drawing the minus gluing of the gamma zeros, I'm just drawing the minus gluing of the tangent vectors. And so sort of that's a loop of tangent vectors that sits at 0, really. So I pulled it out along the axis of R. So this is R here, and that's 0 in the, what is that? Tangent direction to Rn. Right? So, and what's going on? So this is plus xi plus here, and then this here is minus xi minus, anally copied from up there. So, infinite length paths of tangent vectors that sit at my critical point 0. So that's the extra information that sits in both of these curves, in both of these isomorphisms. And I just, Hofer also likes to call this sort of plus and minus together the box gluing. So it's the same, means the same symbol here. So, and I now ought to, I want this operator to take values in my scale Banach space, and I only have something that sits here. So in order to get back, I'm going to use the box minus gluing. I'm going to take the inverse of that box gluing. But that means I need to decide what I'm going to put in the second parameter. So when I'm on the splicing core, the obvious choice would be 0. Because if I do that, then I know I'm going to get back into the splicing core in F. So I actually get a map not just in F, so I get it in the image of pi r. But it's going to be awfully nice to be able to write down this operator for all xi minus and xi plus. So I'd like to actually define it for any pair. And so I'd like to write down something here that's 0 if xi minus xi plus were on the splicing current, something different otherwise. So it's a good idea to start with the minus gluing. So if I was on the splicing clone, then I didn't change anything. So same operator. Right? But I would awfully like this kind of expression to match scale smoothly with this expression here, because they now take values in the same space, f. And in order for that, I should probably not match sort of the 0th order expression with this 1st order expression. So what I'm going to do instead is I'm going to take, I would like to essentially write down the same operator, except it doesn't make a whole lot of sense. I'm taking that same operator and I'm linearizing it. Namely at the curve that's constant equal to 0. So that linearized operator has the form d by dt plus, well, no, sorry, minus the Hessian at 0. And so this guy here, so that's my linearized operator. Because 0 is a critical point, and I'm hoping that it's non-degenerate, Chris is going to like that, that's going to give me an isomorphism between these two spaces. Well, it ought to, because it cuts out, the trajectories that sit, constantly at 0 transversely. It is also of the form d by dt, right, minus some symmetric operator that doesn't even change with time. And that's invertible because that's the definition of this critical point being non-degenerate. So I think, right, I did claim that operators of this type were invertible at some point last semester, I think, when proving transversality at constant Floer trajectories. So I did something that makes it likely that this might be a scale smooth expression, no matter what gluing parameter I have. And it also is very cool because it's an isomorphism between the extra information that I kind of don't really want to care about. So it ties the extra information in the base with the extra information in the fiber. And so that will be exactly what allows me to do a Fredholm theory later on. Yeah. Okay. So it means now that we've seen the example, here's the whole language for it. So let's see. So what I did construct for you was an M-polyfold bundle. Namely, right, we made a surjection between polyfolds. There's some vector space structure going on in the fibers, and I have not just polyfold shards, but actually trivializations of a certain form. Where's the word? It needs to be a bundle retract, not a general retract. And so then we need to talk about what a bundle retract is in general. So here's, right, so what was, well, curly y is equal to curly e, and the fiber over a point e and c plus minus was exactly either finite length functions or broken ones. Goodness, 0, infinity. And I describe this in terms of the splicing that was this capital pi. And this isomorphism was given by this, is given by this somehow anti-pre-gluing box thing. And so, in that world, what my splicing is for the total space is exactly the union over the splicing of the base space and then times these fibers. So that's, again, here, I like splicings because they're very simple versions of retracts. So, let's see. A retract we like to be of bundle type if it has a very nice specific form, which in our case is utterly trivially nice and specific. Right, so this is the retract for my total space, Y or E. Right, so I have this extra fiber F. So on V and E, I ought to just do exactly the retraction that I had, for O, but this was V and little pi VE. And this projection here is just depending on V also. So what I'm looking at is a special bundle retract in which my projection doesn't even, right, it only depends on the gluing parameter and not on the vector that I'm at. So particularly nice form. So no dependency on this whole scale Banach space in which something funky happens in the first component. So main point being here, there is language, right? It is somewhat complicated. The obvious example fits into it trivially. Right. It's the splicing version here. And now I can say what it means to be scale Fredholm. Oops. Different color scheme. So scale Fredholm now again has a couple of sub-words that we need to check out. We need it to be regularizing, which you've heard before, so you should think elliptic regularity. And in a specific trivialization, it should have a Fredholm filling, which is exactly what I already made. But let's see. Oh boy. So this, let's see, this whole section here, right, is again something that is always trivial in the base. And so I want to split that off. So I'm just going to call the thing that maps to the fiber F, little f of V, C. And with that, the formula for little f that I wrote down in the last slide is this one, right? So the two, oh, no, right, plus gradient f became minus gradient f, I'm afraid. So this is the negative gradient flow lines now, right? So both operators on both components when gluing parameters 0, respecting gluing length is infinity, and otherwise operator on pre-gluing, linearized operator on anti-pre-gluing, and then box inverse to get ourselves back into the right space. And so this is a map that's now defined on the whole space here, right? I didn't need to be in the kernel of the anti-gluing to write this down. And so this is what I'm going to call F bar. I don't a priori, if somebody just gives me the section on the splicing core, I don't know how it extends. So there's sort of a choice of that F bar that goes on. And what does that F bar have to satisfy? So here is the Fredholm filling in exactly this language, right? My section is, identity in the base and little f in the fiber, and I've got myself into local coordinates. Somehow, right? Let's forget about this here. In order to be a filling, I actually need a specific retraction in general. In this case of splicings, this is somehow not a condition. So what is a condition, though, is that, right, so this F bar, right, I would like to be Fredholm. So, but that's now, right, it's a map that's defined in this entire space, so I'm going to pretend that we don't have boundary here, so that this is an open set in a scale-Banach space. Right? And then as such, we've already defined the notion of scale Fredholmness on open subsets of Banach spaces. It wasn't entirely trivial, but it is what it is. And then we'd like two conditions here that should imply that the filled thing has the same zero set as the unfilled one. So certainly on the splicing core I want them to be the same. And the other thing that says that if I'm mapping to the splicing core in the fiber, then my pre-image actually was in the splicing core in the base. In particular, if f bar is 0, right, that's always in the image of the projection upstairs. If f bar is 0, then the point lies in the splicing core downstairs, and on the splicing core downstairs I have the same thing. So these two together give me same zero set. And I would like my filling to kind of not add any ambiguity to the Fredholm index. So the last condition is something that has something to do with the Fredholm index. There's some linearized map here, or the linearization of f bar together with the complementary projection. I would like that to be an isomorphism between the complementary spaces. So, in a little more generality, well, let's see. So if I look at the tangent space R times E, that always splits as, right, the tangent space to my splicing core, which we defined as the image of this linearized projection. And so the kernel of the linearized projection is exactly a complement here. So this is a complement of the tangent space of the splicing core, and this here is sort of a complement of the fiber at that point, right? Whatever this point is, here's that point. So this lies in F, right? And F is split into, well, here, the fiber and its perp, which is given exactly by the image of capital Pi and the kernel of capital Pi. So, and right, where you could call this here also the projection perp, and its image is exactly this kernel. So what I'm identifying here is the two complements where really secretly I'm thinking that the linearization of my operator should take the tangent space of this splicing code to my fiber, which is not going to do in general, because it's not going to map into the splicing code. It's going to map to someplace once linearized. But that's made up for by this extra piece, right? The sort of filling just adds things that identify the two complements, and so that's why I then don't really have to worry that my linearized operator of the interesting, nonlinear differential equation is not quite going to map into this fiber. It's going to do something non-trivial on that fiber and hit more stuff. So, I don't know whether this is incredibly satisfying or incredibly dissatisfying. It looks like a very likely, definition of Fredholm. You have this sort of weird fuzzy spaces. You just, extend in some reasonable way beyond the fuzz, and then ask that the extension is Fredholm. So, right, same zero sets, and then you have to check that Fredholmness implies the right things. So, let me just give you a quick advertisement of the regularization, which we're going to say what it means to be transverse. That's going to be completely sort of trivial. And then we'll have these regularization theorems that say, well, if it's transverse, it cuts out a smooth manifold. And then there's going to be a little bit more lengthy, complicated thing that says, well, if the polyfold bundle isn't strong also, and the section was proper, then for some auxiliary norms, some kind of small sections where compactness is controlled will give you transverse things, and any two such transverse things will give you cobordisms. So we'll have to pass that next time.